how the science works. So how does your body work? So you have to eat to survive and gain energy, and differing foods have a different constituent composition with regard to how much carbohydrate, how much protein and how much fat they have within them. If you look at the diagram here on the left, you can see that different types of meal, depending on what they contain, give a different response in terms of what it does to your blood sugar level. For instance, ingestion of a high level of carbohydrate causes a sharp rise in blood sugar, and then insulin kicks in, causes an insulin response, dramatically dropping the blood sugar level. However, if you look at fat, you'll see a much more stable rise in blood sugar over a more prolonged period of time, requiring a less drastic insulin response. So here at the top you can see a white adipose tissue cell, so an adipocyte. White adipose tissue is where we basically store the majority of our fat. So if we see that at the top you have something labelled TAG at the top left, that's triglycerides. Okay, that's how we sort of ingest and transport our fat at the start. What I've done is I've spoken about the insulin rise. If you look at the things labelled green, you can see that insulin promotes the effects of these. So for instance, high level of insulin promotes the effect of lipolipase, or the thing labelled LPL, which basically breaks down triglycerides, TAG, into fatty acids, allowing storage and entry into the cell. High levels of insulin also promote lipogenesis, where excess glucose is utilised along with the entered fat. And then this is esterified to form a stored fat in the cell. However, if you see where I've labelled in red in the diagram, you can see that the stored fat with the large TAG is sensitive to low levels of insulin, and low levels of insulin lead to the activation of enzymes such as hormone sensitive lipase. These break down stored fat into fatty acids and glycerol, and then these are free to exit the cell, and they bind albumin in the blood and are transported as bound fatty acids. However, this is what we want in the cell. We want to break down this stored fat so we have less fat within us. So, if I show you again, it's all about insulin. Low levels of insulin promote fat breakdown for energy generation through things such as hormone sensitive lipase. This is what we want. High levels of insulin promote fat storage and carbohydrate breakdown. This is not what we want. This is back to the diagram quickly to show you. High level of carbohydrate requires a drastic insulin response. So why having too much stored fat is bad for you? It's associated with obesity, which is correlated to heart disease, stroke, depression, diabetes and many more. So if not glucose, then what's the body's fuel? You have beta-hydroxybutyric acid. So during day-to-day function, your brain may preferentially utilise around 100 to 120 grams of glucose. And fatty acids may not cross the blood-brain barrier as they're bound to albumin, as you saw in my diagram of the white adipose tissue. But when insulin levels are low and there's high levels of fatty acids existing in the blood, there's a conversion of free fatty acids to acetoacetic acid occurring within the liver. So here you can see acetoacetic acid in the centre, and it can get converted interchangeably or reversibly to beta-hydroxybutyric acid or acetone. The conversion to acetone is actually irreversible, and you excrete it when you respire, etc. It actually gives you quite smelly breath and sweet smelling urine, which is not what you want. But as you become keto adapted, you become less reliant on carbohydrates, etc., you actually start utilising more beta hydroxybutyric acid and producing less acetone. So beta-hydroxybutyric acid, it can cross the blood-brain barrier and enter the Krebs cycle, so your energy cycle, allowing for the production of ATP, which is a fuel source. Beta-hydroxybutyric acid is claimed to be a more effective fuel source, and there's no diseases associated with lack of carbohydrates. So this diagram, I'd just like to point out that if you look to the far right of the diagram, you see the word ketoacidosis. This is associated with hypoglycemia in diabetic patients, where blood ketones reach around 10 millimolar level, which is often a negative point associated with the diet in terms of media sensationalism. It's probably not that appropriate to the diet. If you look at the optimal ketone zone, you're actually looking for around a blood ketone level of around 2 millimolar. It's sort of like comparing a light shower to a hurricane with a 5 times factor between the two different levels of blood ketone. So this just shows you that producing free fatty acids from triglycerols get converted to ketone bodies in the liver in the centre, and then they can be converted to metabolic, where they're used as metabolic fuels for things such as the brain.